Okay, let's back to the class. Back to class. And let's now we talk about how can you use shared memory for communication. And we also can use the message parsing. So the person A will send a message to this message queue. And person B will receive this message from the message queue. This is the message queue. This message is not belong to A or also belong to B. It's managed by kernel. It's managed by kernel. So it's used by message queue. Message queue. Or we also is you use the pipes. And I don't show the source code now. So you can play with the source code. I will upload the source code later. So we can use the message queue. So one question. Which one is more efficient? If we want to send a very long message to someone A to B, which one is more efficient? Which one is more efficient? Which one? Yeah, both are. If you want to send a very long message, which one is more efficient? Yeah. Why?
I'm not sure. I was going to just
yeah, because you create a shared memory need a system call. System call is very slow, right? But you only need one system call to create this shared memory. And with this memory, you can pass in any messages. So person A write message here, and person B get the message. It's purely memory read and write. But this message passing, you see the message queue, you put one into the queue, you need a system call. Put one message into the queue, into a system call. And the process B also needs a system call to get this message. If the message is really long, it must split to some piece of messages. So that's why shared memory is more efficient. Right? And this is slower because
I was wondering, for shared memory versus the second password, with shared memory goes to be just like share, while it will be like
yes, basically say the message 0, message 1, message 2, message 3. It's a piece by piece understanding. And each kind of memory set is need a system call. We need a system call. Remember that the system call is very slow. Read and write memory is really fast. System call, because the system call, you need the user space must tell the kernel space. Yeah. So I want to do some operations. And the kernel space needs some scheduling because the CPU is busy. Kernel space needs some scheduling to do that. But the memory read and write is fast. Oh, that's a programming trick that's avoid the unnecessary system call. System call is slow. I guess 1 second can run like 1,000 of system call, but it can do billions of memory read and write. Okay, shared memory. Shared memory have a problem of what? Yeah, it's a this condition because this counter increased by 1 is not one instruction set. It's implemented by 3 instructions. 3 instructions. Say this is a counter decreased by 1. It is also need 3 instructions, not 1. So this is possible two memory access can be interleaving with each other. For example, register 1, the counter must increase by 1. And the other process want to read the counters. So they may read all 3 status. And this is not correct. So the intermediate value is not correct. So that's why 2 processes will interleaving with each other. So shared memory, you must keep the sequence. The sequence how can you keep the sequence? So the process A increased by 1, then process B can read. That's the sequence. If the process B read firstly and increase by further is not correct. So this is called synchronization. Synchronization means who is the first, who is the second. And shared memory is how can you control that? Let's say in the chapter 6, synchronizations. Synchronizations always for this shared memory communications. Okay, good. And IPC message passing. This is the message passing. So message passing, we use the pipes. Use the pipes. The pipes. Pipes is not bidirectional. It's single direction. If you want to parent want to send a message to child, the child want to reply some message. Parent, it need 2 pipes. 1 pipes for each direction. 2 pipes. Right. This okay. Not so. Source code is on the on my Jupyter note. And I'll show the code now. And last one is use socket. Socket is in the web network. It can use the IP address. This is the IP address. This is the port number. Use the IP address and the port number to send some message. This is good. This can use the network to send the message. Socket communication, and it also can use the local message. If you local process can communicate with that, it's send to his local IP address plus port number. It's possible, very flexible this ways. But this is use the system call. All the network use system call. It's still slower than shared memory. Okay, good. And you hear it's good. So we finish this chapter 3. Okay, we are fast. Finish chapter 3. We are going to chapter what? Chapter 4. Go. Chapter 4. So, chapter 4. Threads and concurrency. Threads and concurrency. Okay. The motivations are most modern applications are multi-threaded. Don't confuse it. We just now talk about the modern applications are multi-process. And each of the process have multiple threads. And threads running within the application, right? Multitask with the application can be implemented by separate threads. So each thread, so this process can have multiple threads, and each thread can focus on one task, like update display, fetch data, spell checking, answer network request. The threads, all the threads in one process will share the memory space of this process. Right? We know process have an independent memory space. So it's hard. We say it's hard to process communication. Use the shared memories, use some pipes, use some sockets. But all the threads of this process, they share the whole memory space. They can use memory for communication. That's why this is very common used in one process, multiple threads. So process creation is heavyweight, while thread creation is lightweight. Because this is for different purpose. Process maybe it's for different applications. For like this, my PPT slides. This is one process because I don't want the other program to affect my PPT. If my Steam is crash, don't affect my PPT. They must in independent memory space. Don't affect each other. I don't want Zoom to affect the Zoom is crash. Don't affect my PPT. So that's a process having independent memory space. But the thread is lightweight. In this PPT, I want several threads. One thread read and write the file. One thread render. One thread you can do in some send messages. right? They have the same memory space. They don't need some IPC. They don't need the IPC because they already have the shared memory space. All the threads can see all of the memory of this process. That's why it's lightweight. Different purpose. Different purpose. Can simplify the code, increase the efficiency. Yeah. The kernels are generally multi-threads. The kernels are one process. The initial process one, PIE is one. The kernel is one process. So, but the process can have but the kernel have multiple of threads. All of the threads have the same memory space. Yeah, memory space. That's why if one application in the kernel crash, the whole kernel crash, like the one driver. If my USB driver crash, the driver is running on the kernel. So you will see blue screen. In Windows, it's blue screen. Whether in the Mac, will be reboot or some going to other. I never came across that. I always say blue screen. Blue screen is means kernel space crash. So the whole operating system crash. Crash. Okay. That's why user space have a different process to make them independent with each other, not affect each other. This is an important feature of the operating system, modern feature. Okay, important. I always ask these questions in the midterm and the final, and lots of students make a mistake. So that's each thread consists of thread ID. Thread ID is the program counter, the counter, and a set of registers and the stack. Stack is used for what? Here, and because this is a single thread process. Single thread process. The process have a code, data, files, register, PC, and process control, and the stack. All this information under one thread. There's one process and one thread. Okay, this is always used, but this is the widely used. One process, multiple thread, and each of thread has its own PC or program counter. PC is not PC program, and on stack and on register. Okay, and each of thread can has its stack. Stack means it can have a function call. It can be run independently. It can run independently, but it can also access the same code, data, and file. So each of the thread has their own stack. Stack is used to do the function call. They can run independently.
So here, a stack is not a stack of memory. It's not within the memory. That's something else.
It's a stack of memory. It's because there's a stack is used to store the local variable and the function call, right? So with this stack, the thread can run this thread can run independently. So and each of the thread can have a stack for stack and resistance. Look at here. The memory, so we previously showed the memory layout is for this case. One process, one thread. And this is for multiple process, one process, multiple threads. Here. Without the stack, without the PC, without the resistance, okay, this thread run together in parallel with the other threads. It's impossible. If the process can run, it must have a stack. Stack can store the local variable function call. You call a function. How can this thread return and quit this function? It must use the stack. So why I say this is important. Okay. Later I can show some code examples. Okay. Multi-thread examples. So like editing a Word document. Like one thread can interpret the keystrokes. Second thread can display the image. Third thread checking spelling and grammar. Fourth thread can some periodical automatic backup, save to the disk. And you say all the 4 threads have the same memory space. They can access all the memory. They don't need some. They can directly use the memory for communication. They don't need some messages or socket. So this is more efficient because this is one application, right? And this thread crash maybe cause this process crash. So this thread maybe have problems crash, cause this whole process crash. Right? Most operating system kernel are multiple threads, so many threads in the kernel process, and each are doing the special task. One thread can manage the devices, the USB, mouse and keyboard, maybe blueprint, the Bluetooth device, and manage the memories. How can we do the memory allocation, delocation, and interrupt handling, interrupt. Maybe a printer want to print out for send an interrupt. So this is the different threads can do. And even it's one process, but it has multiple threads, it's possible they can run in parallel on multiple cores. Because currently our CPU have 16 cores, 32 cores. And each of the threads can run on one core. This can run in physically parallel, not fake parallel. Scheduling. So one core, when you're doing scheduling, in the one core, 2 threads can run. It's a fake. It looks like it's parallel, but it's not. Like we also call this a concurrency. Later we can discuss it. We will say it's concurrency, not a parallel. Okay, good. The multi-thread server architecture, like a client server, like a client and server. So client will send a request to the server. Like you will log in some website, like our China website. Your desktop is the client. You send a server. No, I want to log into my account. So the server will create a thread. Create a thread to handle your request. And the server process will return and continue to handle the other client. Each of the client will create a thread. Maybe a server can create thousands of threads, maybe 10,000 of threads can handle the request. All the students can log into your account at the same time, right? So this is a very common architecture of the server. The server will not stupidly waiting, oh, the server will process you and process it the other way. No, they dealing with the one shot thread and separate to the maybe 32 cores CPUs. 32 cores CPU will dealing with this in parallel. The one sound thread dispatch to the 32 core CPU, for example, and this 32 CPU can run in parallel. Okay, that's why add another CPU on server, increasing its can handle more requests at the same time. The advantage, responsiveness may allow continuous execution if part of the process is blocked, especially important for user interface. So user interface, like our iPhone. Our iPhone is user interface good. Even some of the process in the background blocked, but the user, some of the threads in the backup is blocked, but the user thread is never blocked. So that's why we have a very good UI experience. Right? UI experience. So UI, that means in the iOS, UI thread has the highest priority for the responsiveness. And the other thread maybe have a lower priority. That's we're feeling that I use the UI is very fluent, very good, never stuck, never freeze. It's highest priority. But other threads maybe reading some files delayed for delay for 1 second, it doesn't matter. And this is resource sharing. Thread share resource by default. Like I said, all the threads will share all the resource of a process defaultly. You don't need to create some shared memory. No, you don't need that. the easier that the process share the result by sharing memory or method passing. Economy, cheaper than process creation. It's lightweight, cheaper than process creation, and lower overhead than context switch. Why is lower overhead context switch? Why? Lower in context switch. Huh?
Not as many process calls, system calls,
Not what?
not as many system calls with context switch.
Yeah. Yes, good. Yes, good. The process must save all his state in the PCB. But threads don't need a saver. Threads only has because it shared all of the resources with the process. It only save part of them into its save part of information for the context switch, not all of them. So that's why I say the thread is lightweight. Scalability, process can take advantage of multiple architectures. Like I said, multiple threads can running in parallel with multi-core CPUs. They can communicate with shared memory. Threads enable concurrent programming and on multi-processor system. Truly purpose. Concurrent means we have on one CPU core, but multiple threads can still run. Looks like parallel, but they are using context switch doing seems parallel, but not physically parallel. Parallel is messed up. Physically parallel. Okay. Concurrency means even one core can doing concurrent. This is a different meaning. Okay. Here has I like this explain of a concurrent and parallelism. This is concurrency. This is a single core. See, with the time T1, T2, T3, T4, 4 threads, and T1, T2, T3, T4, T1. The scheduler, we have a scheduler to schedule this 4 threads. Has a time slice. This time slice T1, this time slice T2. They are running sequentially, but looks like they are running parallel. They are concurrent running. Even though one core they have a different time slice for your running. If the T1 this time slice terminate finish, they switch to T2 use a context switch. Context switch, right? Context switch. That looks like it's a concurrency, but this is parallel. We have 2 cores, core 1 and core 2. See 2 CPU cores. 2 CPU cores CPU core 1 is T1, T3, and the core 2 is the T2, T4. So it's much faster. Double speed up. Right? Double speed, 2 cores, double speed up. 16 cores is the same. Oh, 16 cores is different. Because we only have 4 threads. If we have 4 cores, so 4 threads can allocate to 4 cores. 4 cores can run in parallel, but 16 cores is hard. All the other 12 cores are useless. It's one thread can only allocate to 1 core. All right. So that's all the other cores is waste. Okay. Yeah, good. So it is possible to have a concurrency without parallelism. We have concurrency, but no parallelism. Is it possible? Yes or no? This one? Okay. Let's check your knowledge. Understanding. Yes or no? Don't worry. Just answer my question. Yes. I just ask. Yeah. Yes. This is concurrency, but no parallelism. This is the parallelism with concurrency. Yeah. Good. Multi-core programming. So multi-core programming, multi-core and multi-processor system, like our CPU have 16 cores, and put the pressure to the programmers, challenge. So our programmer must consider about this. So Yeah, it must divide the activities. So if some task is sequential, we must delete it for different task and assign to different threads. They can run in parallel. Yeah, and so let's divide the activities and balance. Evaluate if the task code is run concurrently provides same or more value than the overhead of the thread creations. So thread creation will take a resource. Create threads will never make a calculation. If your program creates thousands of threads, your CPU is busy with creating threads. No resource for calculations. Totally waste. Nothing. It's meaningless. So it's a balance. So your thread is too small. If your thread has only 2 threads on 16 core CPU, it's not enough. But if your thread is too much, CPU is busy with creating threads. Yeah. And the data splitting prevent the threads from interfere with each other. Okay. And the data dependency. So the data must be how can you split the data? How can you make the data independent with each other? So that's doing parallel computing. Test and debug. This is really challenging. So suppose you have a 16 core. So the program not running sequential. 16 threads running together. Can you imagine in your mind? And how can you debug thread by thread, one thread? Okay, you must select, oh, I want to debug this thread. I go into this thread to debug. It's hard. And the result may be affected by other threads. It's really challenging for programming, multi-core programming. I can show you an example. The multi-core programming, this is data parallelism. So the data will split to different cores, different CPU cores. So CPU core 0 will calculate this data. CPU 1 will calculate this data. And because of the good things, they don't affect each other. So if they don't affect each other, it's simple. Finish all the calculations, simple. This is data parallelism. This is the most simple case. Next one is the task parallelism. So the data is cannot split. The data cannot split. You must the task, the whole task will split to the four cores. Like four cores and then they can run in parallel. So can you using your knowledge of algorithm, data structure and algorithm, can you give us an example? Which one can use for this data parallelism? Which algorithm?
Need more security.
Sorry, which one?
Repeat the question. That's a good question.
Okay. You know some of algorithm, some of data structure can use this data parallelism. You know some of them use the task parallelism. Can you give us an example?
The first one was probably for security, like things like you just like that you can if you
Not really. Sorry, no. We're not yet discussing security now. You know. Have you ever doing some matrix adding? Two matrix add together. So the matrix is like a two arrays added together. The data will not interfere each other. Two arrays added together. It's very simple to split it to different cores. Array added, array minus, array A minus array B. Each of item do you add or minus? It's a very simple case. And this one, think about which program, which algorithm is must run in sequential. Sorting. Give you lots of number sorting.
Linked list or something?
Yes, traverse the linked list. It must be sequential. How can you split it to 4 of us? This is hard. As challenge, you must think about another program. Split to 4 tasks. For example, traverse the linked list. Split to 4 tasks. And then merge the result. After the 4 course, merge the result. Maybe you want to traverse the linked list to find the largest value. Right? split the linked list 4 parts and do it traverse. Finally, you must from these 4 results, you must find the largest one. Okay. Because we are operating system code, we are not discuss too much about this parallel algorithm. If you are interested, that's okay. That's a good example. This is a matrix adding. The A is the array, B is the array. C is adding them together. Adding them together. It's good for data parallelism. It's because we just adding them together. Do not interfere each other. And next is find a pair of integer with summation in the file. This is a part. Easy. How can you split the task? Find a pair. Summation is 5. Doing sequential is better. Right? Doing sequential is better. So how can you split? You need some design some different algorithm. Split task, then combine the result. Then like an example, the editing Word document. One thread can already discussed this. Let's see some code. I prepare some examples. Okay, chapter 4. Chapter 4. OpenMP for holding. Okay. Oh, this is Java. So I implement this in Java. I implement this Java. So you see it's called. So that's 2 arrays. The size that's 2 arrays. The 2 arrays with a summer task. I remember it has 2 arrays. Protect with end with left task, summer task. Create a size of a random integer from and then okay. This is doing in parallel. Okay, we'll run the code. We'll say with adding the 2 arrays together. Oh, it's not adding 2 arrays. It's adding the summation of the arrays. Summation of the arrays. So all of the values in the array with some summarize together. We use how many threads? Use how many threads to do that? Okay, I forgot that. How many threads? Fork join. Okay, is a fork join parallelism to use multiple threads. And later you can check out how many threads use. The result here is you see the parallelism only take 32 milliseconds. The parallel summation is this. The sequential takes 34 milliseconds. Parallelism faster. Because and the result is correct. And you must be sure the result is correct. That's because this Mac has 8 cores. I remember 8 cores, right? 8 cores. So in this case, it can run physically in parallel. This one. If not physically in parallel, it's concurrent. It will not have a speed up. It will have cost more time because the CPU will switch the contacts. No physical parallel will not have speed up and even slower. Right? And okay, play with this code later. Okay, good. Okay. This is evidence loss. This is the calculated speed ups. This is a theoretically good speed up. So each of the program, you must find out which one is the sequential part. Sequential running is impossible to split, and which part is parallel, which bar is the parallel running. So S is the sequential portion. It cannot split to parallel. And N is the parallel, N is the number of process calls. Process calls. And Y, 1 minus S is the parallel portion. Parallel portion. It can run in parallel. They can run in parallel. So, for example, if application is 75 parallel and 25 serial, as need this equation, and it's moved to two cores. So two threads can run in parallel. So it's here is divided by 2. As a sequential part, this is the parallel part divided by 2, and can have a 1.6 speed up. 1.6 speed up. This is the theoretical speed up, right? Theoretical speed up. It never, and in real case, it's much less. It should be very, it should be less than 1.6. Why? Why is in real case it's less than this? Okay. Don't forget the overhead of context switch. You create a thread need times. Synchronized threads need times. Thread switch, context switch of thread need times. So this is a theoretical good number, but in real case, you should be very close and never reach this number. And theoretically, you can assume that we have an infinite number of the processor, infinite number of cores. So N is infinity, is close to is infinity. So N is infinity. That means we have very good machine. The cores, how many cores? Infinite number of cores, and we can get a theoretically very good number. Very good number. This is for theoretical analysis. Theoretical, we'll study the course of the algorithm. It maybe let you to analysis the parallel algorithm. What is its theoretical speed up? Theoretical speed up. You can assume that N is an infinite number. You have an infinite number of CPUs. Yeah, here is we have a number of cores. 16 cores can have 16 speed up. It's a idea. Good case. 16 cores can have 16 speed up. Good, perfect speed up. But and assume that N is infinity. So we have a very good machine, infinite number of the processor, multiple of the cores, and your program will be very close to this perfect case, but never reach it. Because this is the S equals sequential portion. This is the sequential portion to 0.05. 0.05. With sequential portion is very less. You can have this kind of speed up. This is the sequential portion is blue is 0.1. 10% is the sequential portion. Have this speed up. This one is 0.5. 0.5 is the half is sequential. Half is sequential, we have this speed up. Okay. Good. That's for analysis of parallel algorithm. Okay. Okay, now as user thread and kernel thread. We can say the user space have a multiple thread, and the kernel space have also multiple threads. Multiple threads, and these threads are put into programmers into the program user thread. The 3 primary thread libraries. POSIX thread. This is the POSIX P thread. This is for libc. The Linux C programming language have this libraries, P thread, and Windows thread and Java thread. In Linux, it don't have a API, directly have API to support thread. Because Linux want to simplify this design. They don't have this original support of the thread. It's always make it complicated, create some thread. So I recommend you do this one. POSIX is libc pthread. The kernel thread managed by the kernel in the kernel space, the kernel thread. So the multi-thread model is actually using the three ways. Three ways, many to one. Let's say the many to one. Oh, this is for like a Solaris and the GUU is a many to one. The user space has many threads, and the mapping to the kernel. And so we use one kernel thread. For example, when many threads have this want to read data or write data into the disk, but the disk is purely sequential device. Yeah, even you have you do in parallel reading or writing to the disk, seems parallel, but you must have a system call to tell the kernel, oh, read the disk, write the data into the disk. It's reduced to sequential. Disk is a sequential device. The disk, SSD or hard disk never support this parallel. Better ways you can have two disks. You have two disks. One thread writing to that disk, one thread writing that disk. That's all. Yeah, this is the all it happened. And this is like a Windows Linux. It's a good as a user space, kernel space that has a user space. The thread can map into multiple kernel space. This is more efficient, right? More complicated, but more efficient. Many. So user space has a multi-thread, use the system call to map into multiple kernel threads. Two level, yes, two level is so just all of this mechanism at the beginning is very simple, but when you dealing with multiple complicated scenario, combine different models, it becomes complicated. Two-level models. This is many to many, and this is directly mapped here. Pthread. I can say it's a pthread is a Linux. It's a project standard API for thread creation and synchronization. It not belongs to Linux itself. Pthread. So that means you must have the libc. Linux don't support this, but all operating systems have this libc. So in Linux, the pthread library implement the one-to-one model. Okay. Okay, let's it's coding time. See some code. So this is use some libc is pthread.h. It must include this header file, and this is one process, right? This is one process. In this one process, this is the init thread and create the thread and wait for the thread to exist. Remember, there's already the main function already have the thread, so each process already have the one thread run, and here you just create another thread, so two threads running at the same time, maybe concurrent, maybe parallel, always parallel. And this thread will execute the function of this runner. So this is the function name. No, not function name. It's a function pointer. Here I declare a pointer. Runner is the pointer point to a function. Here, this is the pointer point to a function. It's the address. And here I pass this passes parameter to this thread. This thread will run this function. Good. Why we must declare here? Because we use it here. In C, you see, we use here. We cannot use a pointer without declaration. We use it here, and we must declare here. And the implementation is later. You can put the implementation here. The implementation is this is the function implementation. And create a thread. After the thread running, as the P thread exists. Oh, this is to summation. You see, this is summation of the I upper. Doing some calculations, summation. Sum is 0. This sum is you see, this sum is a global variable. I guess it's yeah, it's global variable. So it's a global variable. It's belong to this main process. And all the you create a thread. This thread can access this global variable. It's a thread, it's not process. In process, it will duplicate. Process will duplicate. But in thread, another duplicate, it can directly use this parameters. That's why, see, you can access the sum and we print out the result. I can show the code. I can show the code P thread. Like oh, this is the code P thread. Runner. This code. So this my code is little a little complicated. This is child file. Okay. Let's oh, it's a 50. So that's the next class we can show this code. Does you can play this code after class? Oh. Oh. Yeah. It's not shared memory. It's the message. See the source code. See, that's the way to see the source code. I already have set source code. I will upload later. This shared memory. This is a pipe. I don't show the source code. You see, this pipe is you must create a
What is message queue? What does it do?
See the source code.
Okay.
This source code. You see source code. Pipe is this is for FD is 2 pipe. So this pipe system called create a pipe. Create a pipe. And use this pipe, you can say this write data into this pipe. So write data into this pipe. The parent process write data into this pipe. And you don't care about where it's located. It's in the memory.
Okay.
And the parent process can only access through the pipe. And the child process get data, read data from this pipe.
So this shell is pre-searchable.
Yeah. Read data from them. That's the way to learning. Read the source code. Okay.
Yeah.
It's okay. It's enjoy it. It's okay.
Because I have run that, so that's fine.
It's in the slide. I just let you refresh your understanding. Make you understanding well. This is very important. Very important. You must know the layout of the memory.
Yeah, but this is okay, right?
It's okay. That's okay.